Hello everybody. So we've already covered the integration technique, integration by substitution, which I said was like the chain rule backwards. Now we're going to talk about integration by parts, which is like the product rule backwards. This is what it typically looks like in a textbook. You might be thinking that does not really look like the product rule backwards. And we'll talk about both what this means and where does it come from. How can you get to here by starting with the product rule? But I think it's all going to make a lot more sense if we work an example first so that you can kind of see what it's all about. So the concept here is we've got some integral problem, and of course you want to double check first to make sure that you can't use an existing technique that we already know of. But it doesn't look like there's an inner function here that we can apply a substitution to. This definitely isn't an integral that we know already, so we need a new technique. All right, so the idea is we're going to try and match this thing to the left-hand side of this equation. And you'll notice that on the right-hand side of the equation, there's also an integral. So unlike the other techniques we've learned so far, where you match an integral and it just tells you how to rewrite it to find the answer, here you're actually going to rewrite your integral and you're going to turn it into another integral. Okay, why is that helpful at all? The hope is that this is an integral that's complicated that you don't know how to solve, but maybe when you rewrite it, the integral on this side is going to end up being easy to solve, and then you'd apply one more step by solving it, and then you'd be done. So that's what's going to happen here. So we want to fit the parts of this integral to this form. So we're looking for some function u, and then we're looking for a differential dv. dv, when I say it's a differential, what I mean is there's going to be a function v, and when you take the derivative, you're going to end up with something dx. So we're going to try and choose parts from here and make one of these parts be u and make the whole rest of it be dv. All right, so you want to choose your u function to be something that you know how to take the derivative of, and ideally it's going to be something whose derivative gets simpler. So I'm going to choose x to be my u function, and I'm going to choose e to the x dx to be my dv function. All right, you'll see why this makes sense in just a second. So now that I've got my u function, let's take the derivative of that. So du dx equals 1, which means that du equals 1 dx. So all I've done is I've taken the derivative here. All right, so here's my differential. Where did this come from? This came from taking the derivative of my v function. So here my v function must have been e to the x, because that's what's going to give me the differential there. So now that we have all four parts, we've matched what's our u and what's our dv to the original problem. This was u, this was dv. We can use the remaining parts to rewrite our original integral as a term minus another integral. So we know that our original x e to the x dx can be written as u dot v, so our u is x and our v is e to the x, so I can rewrite this as x e to the x, minus the integral of v du. So integral v is e to the x, and then du in this particular example is just dx. Great, so we've taken the integral that we didn't know how to solve and we've turned it into a term and an integral that we do know how to solve, because integral e to the x is just e to the x plus the constant of integration. Really, you're probably thinking minus the constant of integration because we are subtracting the quantity of this, and that's true, but I'm just defining this constant to be the opposite of whatever constant you'd have in here. Great, so that's the answer to our problem, and that illustrates the idea of integration by parts. It's first you have to know this formula, integral u dv equals uv minus integral v du. Then you select which part's going to be your u and which part's going to be your dv. I think it's very helpful to make a little chart like this, because once you've written your u, you take the derivative. Once you've written your dv, you take the integral. Then you have all four parts of the chart, and then you can use that to fill in the rest. All right, so let's do one more example to practice, and then we'll talk about kind of where does this all come from. Okay, so let's try integral x times the cosine of x. So go ahead and make your own chart like this and decide what should be your u and what should be your dv and fill in the rest, and then try and rewrite it. I'm going to pause the video right now. You should also pause the video and you can check yourself in just a second. All right, here we go. So I'm going to make my u function be x. So du is going to be, well, du dx would be 1. So then du equals 1 times dx. dv is going to be my cosine x dx. So this is u, this is dv. Oops, that's not a dot. And then I'm going to take the integral here. So I've got v equals, let's see, what's the antiderivative of cosine? Should just be sine. All right, so now if I take the derivative here, that's going to give me dv dx equals cosine, so dv equals cosine dx. All right, so I've got my table. So that means now I can rewrite this as u times v, so x sine x minus integral v sine x du, so dx. So then that is equal to x sine x minus, let's see, the integral of sine should be negative cosine. So that gives us x sine x plus cosine x plus c. All right, so let's look at where it all comes from. So we'll start, I said this is the product rule backwards, so let's start with the product rule. So here's the product rule. I'm going to go ahead and I'm going to integrate both sides with respect to x. So on this side, because of the fundamental theorem of calculus, we end up with just f of x times g of x. And on this side, the integral of the sum equals the sum of the integrals. So we'll have integral f prime x g of x dx plus integral g prime x f of x dx. So now I'm going to subtract this integral. So I've got f of x g of x minus integral f prime x g of x dx equals integral g prime x f of x dx. Okay, so this is actually the integration by parts formula. It's just got different names. So here we've got f's and g's. And in the formula I showed you on the first page, we had u's and v's. So here's how you get from here to there. We know that in the original integration by parts formula, we had uv minus v du. So let's rename u as f of x. So let's rename f of x as u and g of x as v. So I've got u equals f and v equals g. And then if I take the derivative of each of those, I've got du dx equals f prime. And then we move the dx over to make it a differential. Same thing here, dv dx equals g prime, so dv is g prime dx. And so now that lets us make some substitutions. So we've already got f times g ends up as uv. Notice that we've got an f prime dx, which is the same thing as our du, and g was our v function. So we've got v du. And then over here, we've got a g prime and a dx, so that's our dv. And we've got our f function, which is u, so that gives us u dv. So this is the one that I showed you on the front page. Integral u dv is uv minus integral v du. And you can see that it follows directly from the from the product rule formula. All right, let's do one last example. Let's do x squared cosine x. So like we did before, go ahead and choose your u and your dv. And I'll be here in a second when you're done. Go ahead and pause the video. Okay, I'm still here. So I think it's going to make sense to make this x squared and this cosine x dx. We'll take the derivative here, and that gives us du equals 2x dx. And we'll take the integral here, so that gives us v equals sine x. So now we can rewrite this original equation as uv, so x squared sine x, minus the integral of v du. So the integral of sine x times 2x dx. So I'm going to write the 2x here and the dx there. All right, great. So this is not a formula that we obviously, sorry, this is not an integral we obviously know how to solve. Of course, I can take the 2 to the outside. But you might notice that this is actually very similar to the first example that we did integral by parts with. So let's just do integration by parts a second time. So I've got u and a dv. So my u is going to be x. My du is dx. My dv is sine x dx. So that means my v is negative cosine x. So again, I've made my little chart. And so now I can rewrite this. But here I'm going to write it all down here so that we can be a little more careful. So minus 2 times, all right, so I'm trying to rewrite this integral. Note, you will be in danger unless you actually put your grouping parentheses here, and I'll show you why once we've written this out. So I can rewrite this as uv, so negative x cosine x minus integral v du, so v is a negative cosine, so I'll turn that positive cosine x dx. So rewriting it all again, x cosine x. So the integral of cosine, of course, is just sine. So that gives us sine x plus our constant of integration. And now we want to distribute everything and kind of make it look nice. So x squared sine x plus 2x cosine x minus 2 sine x plus, it's really minus 2c. Here, let's do this. I'll make this c0, and then I'll make this be plus c1, where c1 is negative 2c0. Yeah, that's fine. So there you go. That might have seemed a little bit lengthy to you. It's actually not so bad. I want to try and raise your threshold for what you consider to be messy. But that's it. We've integrated by parts. And you can keep doing that. Obviously, if we had x, well, maybe not obviously, but if we had x cubed cosine x, we could integrate by parts. That would give us an x cubed minus, and then we'd have an x squared, and then we'd integrate by parts again, and then we'd integrate by parts again. So you can chain these together. All right, that's good for the moment. Come back in the next video to see another wrinkle that might occur when you have an integration by parts on a particular kind of example.